everyone. Today we will be answering some transmission line problems, and we will try to understand how these solutions came up. Okay, so we begin with the number one. For a given length of a coaxial cable with distributed capacitance, C is equal to 35.05 nanofarads per meter, and distributed inductance L is equal to 44.28 picohenries per meter, determine the velocity factor and velocity of propagation. So first, we need to know the velocity of propagation to find the velocity factor, and the formula of velocity of propagation in terms of uh, inductance and capacitance is equal to 1 over square root of LC. Okay, so just input the given values. That is 1 over square root of quantity. The inductance is 44.28 here, 44.28 times 10 to the power of negative 12, as it is a pico, no? Multiplied by 35.05 times 10 to the power of negative 9, because it is nano. And just simply input this into your calculator, and it will have an answer of velocity of propagation is equal to 802.698 times 10 to the power of 6, so that is meters per second. Okay, since we are finding the velocity. And next, we find the velocity factor, that is the ratio of velocity of propagation to the velocity of light. So since we have found the velocity of propagation, we just want to input it in here in the formula. So that becomes velocity factor is equal to 802.698 times 10 to the power of 6 meters per second over the velocity of light, that is 300 times 10 to the power of 6 meters per second. And the units will cancel, so velocity factor will have no unit. So velocity factor is equal to 2.676. Moving on, we have number 2. A very low loss cable has 4 picofarads per feet of distributed capacitance and 25 nanohenries per feet of distributed inductance. Calculate the following. So A, the capacitance of 40 feet length of this line, the characteristic impedance, the velocity of propagation, and the ratio of the shield diameter to center diameter of the coaxial. So first, we want to find the capacitance to the 40 feet length of this line. So in a 40 feet of length, what is the capacitance of that? So it is simply capacitance will be equal to, since we have the given value 4 picofarad per feet, okay, of distributed capacitance, so we just simply put 4 picofarads per feet multiplied by 40 feet, since we are calculating the capacitance over 40 feet of this line. So simply, capacitance will be equal to 0.16 nanofarads, okay, for the 40 feet length. Next, the characteristic impedance, it will be calculated in terms of L, or the inductance and capacitance. So the formula is characteristic impedance is equal to square root of L over C. So simply input the given values, that will be equal to square root of 25 times 10 to the power of 9 henries per feet over 4 times 10 to the power of negative 12 farads per feet. And the feet will cancel, and just simply calculate this with your calculator, and the characteristic impedance will be equal to 79.06 ohms. Okay, since we are asked of the impedance. So letter C. So we have a similar formula from number 1. So again, the velocity of propagation will be equal to 1 over square root of LC. So simply input the given values. So that is 1 over 25 times 10 to the power of negative 9 for the inductance, and 4 times 10 to the power of negative 12 for the capacitance. And simply calculate this, we will have 3.16 times 10 to the power of 9 feet per second. And we wanted to convert this into meters per second, so just simply multiply it by the conversion factor, which is 0.3098 meters per feet. The feet units will cancel, and we will be left with meters per second unit. So the final answer, velocity of propagation, will be equal to 963.86 times 10 to the power of 6 meters per second. And lastly, the ratio of the shield diameter to center diameter of the coaxial. So we have the following formula in terms of the ratio. This is the ratio that we are talking about. So this is the shield diameter, the big letter D, and the center diameter is the letter D, or small letter d. So the formula here, we have a formula here for characteristic impedance that is equal to 138 over the square root of E sub r, or the permittivity, log d over d, or simply it is equal to 138k log d over d, because k is equal to 1 over square root of E sub r. So they are all equal. This is equal to each other. I mean this. So in order to calculate this one, okay, we first need to calculate the k. So k, or 1 over square root of E sub r, is equal to the velocity of propagation over the speed of light, c. So we have found the velocity of propagation as 963.86 times 10 to the power of 6 meters per second. So just simply input it in here over the speed of light. And the answer is 3.213 for the k. And since we found the k, we are now complete in values so that we can find the ratio. So we have the characteristic impedance, that is 79.06 ohms. So simply input in here the formula is equal to the k. Okay, k here, k times 138, and then log d over d. Okay, by some algebraic manipulation, we divide both sides by 3.213, and it becomes like this: 79.06 over 3.213 log d over d to the power of 138. So by rules of logarithm, the coefficient will be an exponent, okay, with the rules of logarithm. And we want to eliminate the logarithm, so simply raise it into this number, or 10 raised to this number, okay, since this has a base of 10. Okay, so this becomes 10 the power of 79.06 over 3.213 is equal to the ratio to the power of 138. So the logarithm is eliminated. And we are left now with the ratio. So we just need to eliminate this exponent. So exponentiate both sides by 1 over 138. So this will be eliminated. As we can see, it is left with d over d, and the left side will be multiplied by an exponent of 1 over 138. That's why we have a denominator of 138 here. So just simply calculate this into your calculator, and the ratio will be found as 1.508. Okay, so moving on with the next problem. Here we have number or problem number 3. Calculate the actual length in feet of a half-wavelength coax with velocity factor of 0.86 at 300 megahertz. So we have the formula. The length is equal to the wavelength over 2, since it is a half wavelength coax. Okay, and we since the wavelength is equal to v over f, or the velocity over frequency, let me just because this is seeing f. Okay, so wavelength is equal to v over f. Okay, so it becomes the length will be equal to v over 2f, or since we have velocity is equal to the velocity factor times the speed of light, so we have kc over 2f. Okay, so just simply input the given values. So we have k as 0.86, the velocity factor, multiplied by the speed of light, 3 times 10 to the power of 8, all over 2 times the frequency of 300 megahertz. So that is 300 times 10 to the power of 6. Okay, and here we multiply it by conversion factor 3.28 feet per meter. Okay, to have an answer with a unit of feet. So the final answer will be length it is equal to 1.4104 feet. Okay, because the answer here will be in meters, since we are asked for the actual length in feet, we multiply it by the conversion factor. Okay, so this is the final answer. Moving on with problem number 4, we have a 500 line is terminated by a load of 10 minus J15 ohms operating at 100 megahertz. Reflection coefficient is 0.45 degrees, 16.56 degrees, or angle 16.56 degrees. Find the SWR, position of the first voltage minimum in meters, the position of the first voltage maximum in meters. So to solve for the standing wave ratio, that is equal to 1 plus the absolute value of the voltage reflection coefficient over, or all over, 1 minus the absolute value voltage reflection coefficient. So the voltage reflection coefficient is this one. Okay, that's 0.45. So simply input SWR will be equal to 1 plus 0.45 over 1.045, or 1 minus 0.45. So calculating this, we have the standing wave ratio is equal to 2.63. Next, the S sub minimum, that is equal to the phi, angle phi, plus quantity n multiplied by 180 degrees all over 2 beta. So we find beta as equal to 360 degrees over the wavelength. And since the wavelength is equal to the velocity of light over the frequency, okay, so that is 3 times 10 to the power of 8 divided by the frequency 100 megahertz. So 100 times 10 to the power of 6, that is equal to 3. Now simply input the datas, that is equal to 16.56 degrees phi for the phi, plus 1 since we are finding the minimum, times 180 degrees all over 2 times beta. So we have the S minimum is equal to 0.819 meters. Okay. So for letter C, the S sub max, or the position of the first voltage maximum, is equal to the angle phi plus quantity m multiplied by 180 degrees all over 2 beta. So again, we have beta is equal to 360 degrees over the wavelength, and wavelength can be found as the velocity of light over the frequency. Okay, here. The same with here. So again, it is equal to 3. So inputting the values, we have S sub max will be equal to the angle here, 16.56 degrees, the angle of the reflection coefficient, plus quantity 0 since we are finding the maximum. So if we are finding the minimum, the n is 1, and if maximum, the m is 0. Multiplied by 180 degrees all over to beta. So we have beta is 360 degrees over 3. So simply calculating this one, we have S maximum is equal to 0.069 meters, or the position of the first voltage maximum. Okay, moving on, we have the last problem, number 5. A transmission line has a characteristic impedance of 60 ohms and a reflection coefficient equal to 0.844 angle 80 degrees. Find the load and the SWR of the line. So we are asked to find the load. So we can use this formula to find the Z sub L, or the load. So that will become, or the formula we will use is the reflection coefficient is equal to the Z sub L minus the characteristic impedance over Z sub L plus characteristic impedance. So the reflection coefficient is given as this one, 0.844 angle 80 degrees, is equal to Z sub L minus 60. The characteristic impedance is 60 ohms, all over ZL plus 60. So first we need to convert this polar form of reflection coefficient into a complex number. So in order to do that, we simply let A is equal to be the real part, that is 0.844 cosine 80 degrees. Okay, so the real part is equal to 0.1466, and the imaginary part B is equal to 0.844 sine 80 degrees. So that is equal to 0.8312. So we have here the complex number 0.1466 plus J 0.8312. This is now the reflection coefficient. And again, the right side will be the same, ZL minus 60 over ZL plus 60. And by algebraic manipulation, divide both sides, or multiply both sides by ZL plus 60. So that becomes ZL plus 60. Quantity 0.1466 plus J 0.8312 is equal to ZL minus 60. Okay, or by just simply cross multiplying. And by distributive property, distribute the terms. So distribute this one, and then this one, and then this one. So we have 0.1466 ZL by multiplying this, plus J 0.831Z, or 8312 ZL. And again, this one, multiply, so that becomes plus 8.796, and lastly, multiply these two terms, plus 9.872. And again, the right side will be equal to ZL minus 60. And we isolate the terms with ZL variables in the left side and the rest in the right side. So that becomes 0.1466 ZL minus ZL. So we transpose this ZL onto the left side, plus J 0.8312ZL. Just copy this one. Is equal to negative 60 minus 8.796, transpose this into the right, and minus J 49.8792. Again, transpose this one. And factor out or combine the terms. So by combining these two terms, subtracting them to each other, this becomes negative 0.8534ZL plus, copy this one, J 0.8312ZL is equal to, okay, we can combine these two terms, negative 68.796 minus, just copy this one, J 49.872. And again, by factoring out the ZL term or ZL variable, so ZL quantity negative 0.8534 plus J 0.8312 is equal to, just copy the right term again. And by isolating the ZL, divide both sides by these two terms. So it becomes ZL is equal to negative 68.796 plus J 49.872 over negative 8 or 0.8534 plus J 0.8312. So we use conjugate base. Okay, so multiply this by its conjugate. So the conjugate will be negative 0.8534 minus. Okay, we use minus because we are using the conjugate. Minus J 0.8312 over the same with the numerator. So this is equal to 1. And by distributive property or multiplication of fractions, just multiply these two, and the answer will be equal to 17.256 plus J 99.74 over 1.4183. And again, divide these to 17.256 divided by 1.413 will be equal to 12.167, and divide this 99.74 divided by 1.413 or 1.4183, so that becomes 70.32. So the final answer, ZL or Z sub L, or it is the load, is equal to 12.167 plus J 70.32. Okay. And now the standing wave ratio of the line. So again, it has the formula SWR is equal to 1 plus the absolute value voltage reflection coefficient all over 1 minus absolute value voltage reflection coefficient. So the voltage reflection coefficient is given as 0.844. Then we can easily substitute this value into the formula. That becomes SWR is equal to 1 plus 0.844 all over 1 minus 0.844. And by simply calculating this, we can find the standing wave ratio is equal to 11.82. Okay, so that's all of the problems, and I hope you've learned something about these example problems, and thank you very much for listening.